the talk, you do know what it is. So let's get started. So whenever, I give a lot, not a lot, but I give quite a few talks a year to primary school children, to high school children about why I'm a female scientist, why do I do science, why I studied physics, why did I do this? And most of the time, the kids ask me, like, did you want to become a scientist since you were like a child? And the answer is no. I didn't even know what science was. No, the answer is like, no, I didn't know. I just like started studying physics. I don't really know why. I mean, there was this sort of like advanced exams for physics that some high school kids took, and there was like this like Olympic games of physics. And I passed the first one and didn't qualify in the second because I made a very bad mistake. I still remember it. And I thought like, well, maybe I should be studying this because really I'm not very good at this. So I don't know, it's probably still working. Okay, so I just decided I'm going to study physics, I like it quite enough. So I'm going to do this. And I actually wanted to study astrophysics, but then after taking my first astronomy course, I thought it was the worst thing I had ever done in my life. So I said like, no more astrophysics for me. I'm going to try to find something else. And then I found electromagnetism and I thought, okay, this is kind of cool. But a year later, I had my first course on statistical mechanics and I thought, oh God, now I think I like this a lot. But I didn't start doing this. I think it was some point in my second year or third year, I had this professor, you don't know what this is, but I'm going to tell you about it. So, who was doing solid state physics, and he was teaching quantum physics. And he said, oh, why don't you come to my lab and you can do this and that? And I was like, oh, well, this is such a nice opportunity. Maybe I should do it. So I went and I started a PhD on quantum tunneling. So what I'm showing you here is like a molecule. This is what's manganese acetate 12. So these are like what are called molecular spins, and this is the magnetization. So like a magnet, as if you increase the applied magnetic field, increases the magnetization. And in here you see like these different jumps. I don't know how to point at this so that people at home will see it. Oh no, the mouse is not working. Well, anyway, so you see that there are these little jumps. This is because at every so often the levels of the different spin numbers like resonate, and boom, you have like suddenly a sudden change in magnetization. So I was studying this, but after a while I thought like, you know what? I didn't really like this. I was doing experiments and just like powdering things and growing crystals, and I thought like measuring with these very low temperature things, and I was just like, my heart is not in it. So I decided to change things, and study something else. Well, not everybody has the opportunity to do it, but I did because I just wasn't happy with what I was doing. So my first lesson here was like, if your heart is not in it, like if you can, just don't do it. Like we will come, probably many of you have experienced this already, but really if you're not in love with what you're doing, maybe you shouldn't be doing it. Well, that's what I decided. So I decided to change gears and I went to study something else. Does it look familiar to any of you, this kind of plots? Has any one of you seen them before? Who? Can you raise your hands? Some of you. What does it remind you of? Crazy matrix. Well, more than crazy matrix. Something more specific? Correlation matrix. Mm-hmm. No? 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 What did you say? What did you say? It's replicas. Yes, it's the Parisian sets. This is the replica symmetry breaking that Giorgio Parisi did. These are the plots, like a new version of the black and white plot that he did when he published his paper. So I wanted to have a PhD in spin glasses. So I don't know if you know what spin glasses are, but what happens is that you have this sort of like magnetic systems with spins. They have different kinds of interactions, and what happens is that, I don't know if you're familiar with this plot, so I'm plotting the susceptibility versus the temperature. When you have a regular ferromagnet, at high temperature, you have a paramagnetic behavior, and when you are below what's called the Curie temperature, then you have a ferromagnetic behavior, and the susceptibility, which is the change in magnetization when you change the magnetic field, increases. Now, in spin glasses, which is the experimental plot that I'm showing you below, this thing doesn't happen. So you have paramagnetic, and then you have like, I don't know what this is. At the time, this is experiments from the 80s, I don't know what this is. And people were trying to understand what was happening and trying to find an order parameter for this. And what Giorgio Parisi did, and this is why he got the Nobel Prize last year, was he found a mathematical framework to explain to formulate the order parameter of these transitions. Cool. So I spent most of 4 years, not 4 years of my life, a little bit less, like working on spin glasses. Now, how did I like it? Okay, I already explained this. So my PhD was, my choice, because I decided to go to something very theoretical because I wanted to learn theory. I was like, what am I doing here doing experiments? I did all these theoretical subjects for nothing here. No, I want to do theory. But I also have to say that that community wasn't very welcoming, and it was making it very hard for students. There were no events like this where like somebody will come and explain you like the fundamentals of spin glasses. They would just give you their talk for like very smart people, and you would be there and thinking like, I don't understand anything. So it was 3 years of my life in which I was mostly going to conferences and thinking, I don't understand anything of what these people are saying. And I started thinking like, maybe I'm not good at it because other people seem to be doing okay. No, they are understanding things. I mean, with time, I think that you learn that sometimes it's perception, like you think you're not understanding, but people outside from you, they're thinking, well, she's not doing that bad. I mean, she's kind of okay. But I was actually hating it a lot because I was thinking, really, I mean, this is so tough. I mean, half of the time I don't know what I'm doing. And it's awful. But, well, so then still, I said, let's go for a postdoc. You know, maybe there is still something out there that I would like to be doing. And maybe there is something, I wanted to think, there is something I have learned here all these years that will actually carry on and will help me become a better scientist. So, you know, a lucky happening is that, you know, last year they gave this Nobel Prize to these two people working on climate science and to Giorgio Parisi, who, as I said, was, I guess he had this ability to think in original ways about math and on how to use math to solve like statistical physics problems. And the reason why he got this Nobel Prize is not only because of what he did, right? It's because of what the people who came after him were able to do with what he had developed. So they applied his framework, let's say, to like computer science problems, to DNA folding problems, to all sorts of problems. And this is what, I don't know, got him the prize, I think, and not only what he did. Well, anyway, but when he got the prize, right, I was very happy, right? And then, you know, the newspaper in Tarragona asked me to write something about it, and somebody else asked me to write something about it, not only because I had worked on spin glasses, because also because Parisi was the thesis director of my thesis director, right? So I had met him and well, whatever. So I went to Rome and I worked with his lab and like all these things. And still I was feeling like I wasn't good enough compared to these people. But anyway, when I look back now, right? And I hope that by the end of my talk, you will see this, like there is really like so many things that I learned from that period that I have been able to use. So, I mean, this idea of, you always find this moment, it was like, I think I'm not understanding anything, really, I suck at this. I mean, I don't even know why I'm trying to become a scientist, but you actually probably are much better than you're giving yourself credit for. And there are always going to be good things that looking back, you will remember and think, okay, this was actually a good moment. And then I learned to do this. So that was my lesson. I say lesson N because this is lesson N always. When I look back and think, actually, this was pretty good. And why didn't I recognize it at that time? So probably you should, everything that you do, you should like stop and think like, actually, this is, you know, this is a nice piece of work, regardless of what other people are saying. And I will come back to this later. Okay, so I went to have a postdoc. So, and I wanted to do something biologically related. I mean, don't ask me why. Well, I had always liked biology, but when I wanted to study, I wanted something more quantitative. And I went for physics, but I didn't know, what am I going to do? Am I going to go for like brain science? Am I going to do ecology? Am I going to do like more molecular biology? Well, I ended up working going to Northwestern, working on something called microarrays. Which one of you has heard about this before? Microarrays? Do you know what a microarray is? No? More or less. So this was early 2000s, right? And at the time it was super hot, like the first sequencing of DNA that was cure every single disease. It hasn't happened, but that was what we were thinking at the time, 20 years ago. Hasn't happened. Oh, but that was the time, like first sequencing. And then there were this thing called microarrays. Everybody was like amazed. Simultaneously, in this like little thing with like little wells, you could probe thousands of genes at the same time, right? So the idea of this was, it was this sort of competitive essay, right? In which you would have like, you would want to know gene expression in cells. Now we have much better ways of doing this, but you would want to know gene expression in cells, a diseased population and a control population which wasn't diseased, and you chop them up, right? And you tag them fluorescently. And then in each one of these wells, you would have different strands that could recognize the chopped strands that you had in your population. And then you would just try to see which population had the larger fraction of RNA, say, it could be DNA or RNA of a certain type. And then because they were fluorescently tagged, you could see, you know, with these colors here, if it was green, then diseased one has more. If it's red, then the control population has more. If it's yellow, then both have the same sort of thing. So everybody was like, wow, this is like the future. We can do so many things with this. Now, no one here knows what a microarray is because nobody else is using it. But at the time, the problem was like, how can we distinguish what thing is connecting to another thing? So I went to work on a problem of RNA folding. Like, whoa, who, like maybe Susanna would tell me about this. Eh? You know this paper, it's like a review. Yeah. I just said this image is nice. So I went to work on RNA folding and building like statistical mechanics methods for RNA folding here and there. And to my dismay, like I worked maybe 2-3 years in this, and there are papers that I have not been able to publish because it was a very close community who were like absolutely hating what we were doing. And it was hard, and people were like, where are they going? I mean, these methods that they use, they are not going to work. These models in a lattice, I mean, blah, blah, terrible. And I was growing very frustrated. It was like, okay, I've been here working on this for 2 years. I'm learning C++ for nothing. I mean, like, come on, I mean, like, what's going on? So, well, but I still like, I'm a very stubborn person and I'm very, what's the word? I'm very persistent, that's the word. I'm very persistent. It's like, well, you will not stop me. I will keep doing this if I can. Well, but then something happened. So I was in a lab at Northwestern with Luis Amaral, who was, well, I don't know if you know him personally, but he has like as many interests as there are like plants in the earth sort of thing, right? So he wants to do this and he wants to do that and he wants to do all sorts of things. And probably this is why I want to do so many things too, because I was in contact during my years as a postdoc with so many different problems. And he was like, oh, you know what? I mean, we are doing this thing in networks. And I was like, no. I don't want to work on networks. I want to be working on these things because this is what I really wanted. This was my choice. It's like, yeah, but we are trying to do this. Well, let me go after this. So we are trying to do this thing and we don't know exactly how to do it. And maybe you can help us. And I was like, no. I want to keep going, right? And he said, yeah. So yeah, that's good. But I mean, you're hitting a wall. I mean, it's not going to happen. Really, I'm doing everything I can. It's not going to happen. We have to find something else. And I was like, what do you mean something else? Like, yeah. He said, like, you know, lesson learned. This is tough, but you have to know when you have to step back and like maybe do something else. You have to be persistent, but not too much because then time is gold, right? And yes, I was saying the papers that I never published, reviewers were extra mean. I was just like, I was telling English, but I mean, this doesn't work. They're complaining so much. It's like, I mean, they just don't like it. I mean, it's just like this irrational thing about people not liking what you do despite it being objectively correct, right? It's not like we're going to publish in Nature, but I mean, you can publish somewhere else, right? This is good work. And so it's like, well, this is not the way always things work in science. This doesn't mean that you have to do like I did and not publish those results just out of frustration. But I mean, well, so these things happen. This doesn't mean that it's the end of the world. It's just that you have to accept, okay, defeat, if you want to put it in this way. Well, so about the network problem, the networks problem, and here I am, right? So he said, we have this problem, and at the time, right, this was early 2000s, people were very excited about this. So modularity and how to describe large-scale structure of networks. And I was like, well, this is like a nice idea, but I don't know how I can contribute to this. And I was like, yeah, because we have this model and blah, blah, and we have to do these analytical calculations. And this is going to sound very funny because, I mean, in networks, it's not like we can always do analytical calculations, but there were some things that could be proved about some properties of this modularity function. And I said, oh, actually, I know how to do this. Actually, there are some spins models, blah, 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 and I know this can be done. Okay, cool. So now I published this one paper in about like understanding how like modularity is not an absolute measure of anything, but it's something that it's relative, and it can just be like a random event, say, come out of fluctuations, as we said in this paper. So this paper is old, but it's a very interesting paper for those people who work in network science, because it just showed like, well, unless you do something very rigorous that I will not have time to explain here today, and you say something like probability theory to estimate goodness of your model, probably this is quite arbitrary, and you have to be careful, because maybe some network, like a random network that shouldn't have the properties that you want it to have, like having modules, has them just by random chance. So you have to be careful. Now, talking about reviewers, I mean, don't get me started. I mean, this paper has had like a lot of citations, a lot, like more than 1,000. And this is in PRE, it's like, but we sent it first to PRL, and we got these reviews about this problem has already been solved, which is like, okay, this problem has already been solved. I mean, no, it hasn't, but it has already. We had other reviews about you have demonstrated that this network has modularity, but this is impossible. This kind of things. It was completely crazy. I mean, so it was bad, but it was because of people at the time, they didn't know about this at all. They didn't know this problem at all, and they decided that it was simpler than what it was actually, than what it actually was. Well, anyway, that's history. I mean, the paper still did well, and I was very happy to contribute. But then, right? And so my lessons here. So, yeah, go ahead. You did.
So I'm curious, what's your opinion as one of the thousands of paper on methods based on maximization of modality?
Oh, well, I think they shouldn't. I mean, okay, so I think we have come a long way. This was early 2000, right? Now we are 20 years later, not quite, but almost. And I think we have better methods to address this problem.
In practice, in applied papers that apply network science to something, people can easily like down.
Yeah, I would not recommend. Now, that being said, I would not use it. I don't use it. Like, I don't use it because I think there have been developed Bayesian methods to answer this question in a way that modularity cannot. Now, that being said, depends on the network. It depends on what you want to do with a network. Okay. Now, if it's something and you want to do, say, conclusions based on inference of the parameters, then don't use it. If it's a descriptive thing of your network, then you can use whatever you want, whatever suits your needs, right? But I mean, if you want to draw conclusions based on like the parameters that you inferred from that, then I wouldn't use it, because I mean, they are not the best parameters that you could find necessarily, even though sometimes they might be the same, but you are not sure. So if you want later, I can. I don't want to like, but I mean, when I give like, I went to a summer school in Como, and I had lectures on this, and they were horrified. Like, okay, then I can throw it to the, paper basket kind of thing. And I said, like, no, I mean, well, you have done this now, but now you can do something better the next time. Okay. But yeah, thanks for the question. Well, anyway, so based on these referee reports, so sometimes reviewers, and this will happen to all of you, they are clueless. They don't know. They read it. They don't know. They are not experts. and they say the first thing that comes to their minds. And that is not, it's unfair. I know it's unfair for you, it's unfair for me, it's unfair for everybody, but I mean, that's the way it is. And you just have to learn to read those papers, not as a personal attack, but as something that comes with the job. Now, another thing, besides being able to learn to handle rejection, when you're a reviewer, try not to be mean. Please, 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 please. I mean, why am I saying this? So I'm an editor for different journals, right? And I send and I ask for people for reviews, blah, blah. And the young people are always very harsh with other. So I recommend that, you know, you read it, right? Not always, but often say. Not always, not always. Some are nice. But write a report and then just leave it for one day and then come back and read it and say, like, you know, if somebody told me this way, I mean, would I like it or not? Because there are different ways of telling people no, right? And you don't have to say like, no, this is crap. I mean, nobody writes this, but I mean, just to get the idea. Even though I got once I got this referee report in which they said, this is not even wrong. This is not even wrong. Can you imagine? This is not even wrong. It's like, what? And how can you write this in a referee report? Well, anyway, I don't know who that person was, but I mean, that person didn't have probably wasn't having a good day. I don't know. This is not even wrong. That's very, I don't know, it's kind of offensive, don't you think? Well, anyway, I'm still here. So, I mean, I just like, well, whatever. Okay, so going back to my networks, and I mean, this is going to take very long. Well, let me see. I try to speed up a little, because if not, I'm not going to get to the machine scientist. So then I said, okay, so maybe there are things that I can do on networks, right? And actually there was this nice, so this thing that I still remember, and that it sort of gave sense to what I was doing. So no, I don't want to show you this here. So this was 2005, and Science Magazine published this special issue on what we don't know. And there were these 125 questions, unanswered questions in science. I should go back one day and see how many of those have been answered in the last 20 years, probably very few. But there was one, right? So remember, it was like early 2000s, there was like the boom of high throughput technologies in biology. Now we can like have sequence things. Well, maybe RNA-seq wasn't ready yet, but I mean, well, anyway, we could sequence things. We had like lots of data out there, and we had done very little with that data. Probably we still have done very little with the data, but at least we have done something. But one of the questions was like, how will big pictures emerge from a sea of biological data? So the thing is like, so we have all this data and we're not doing anything with it? I mean, maybe we have to try to find ways to understand all this data, right? But what's happening is like, people had microarrays with thousands of genes, and then they would look at the genes that I already knew that I thought were going to be important. And I see that it matches, right? And they were learning this in this very incremental way. And they were calling for like, well, but we have to learn from this as a whole, right? So that was the time when like systems biology started to appear, right? Can we look at this data from a holistic point of view, as opposed to like from a bottom up kind of approach, more molecular biology like. So and now I'm going back and forth. So then so the problem that we wanted to see in networks, right? Was that, so these two networks are the same network, right? But if I show you the left one only, there is no one here that would be able to tell me that this was an airport connection network, because you just don't know what that is, right? But we wanted to see if there was some property of the network, right? That only from the connections I could sort of like know the relationships between these nodes, right? This is sort of related to like the modularity problem, but we wanted to have this sort of like hierarchical view. Now we use modularity, we can use other things now, right? But the idea was that using some sort of modularity approach, right? And understanding that there is more than one partition of your nodes that actually is explanatory of your network, right? You can get a lot of information about which nodes are closer to others in the network. And from this, you can get sort of like topological hierarchies. Like, so in here, in B, right, in this, you see like the different colors of the nodes, right, correspond to nodes that are like together at the top level in my hierarchy. And this correlates kind of well with geopolitical, say, relationships between the different countries. Now, I think it's funny to say this here, but do you know what? When you go down in the hierarchy, and this is not shown in here, do you know where Palma wasn't classified with, say, like other airports in the Spanish peninsula, in Spain, in the peninsular airports, say. Palma was classified with Germany. I thought it was super funny at the time. Whenever I explain this, people are like, what's Palma? And I'm like, no. So today I get to say this here and everybody understands why this is the case. Well, anyway, no, I came once to IFISC a long time ago and I said this and I say, are you serious? I'm like, yeah, I mean, it has so many more flights going to Germany than to any other place. Well, that was at the time. I mean, now this data is old. Well, anyway, so the thing is that so now what I liked a lot about this problem was that I got to use a lot of concepts that I had learned during my spring glass phase. I know about like landscapes that are very hard to like, for which like the optimum is not clear, how to handle that and everything. That's something that I used from my training to solve this problem and to get this, actually this paper was published in a nice place. My thing is like, so sometimes nice things do happen, right? This was a particular nice thing, even though this was the paper that I got this is not even wrong, review when we sent it to Science, and it almost got accepted, and it didn't because the reviewer thought that it was not even wrong. Well, anyway, it was published somewhere else, and it's still a nice paper. And it's still nice, and I still remember it. And I think that for me, at that point was like, oh, actually, there are so many things that I could do here, applying everything that I learned during my PhD to other sorts of problems that actually people think about and are interested in them, as opposed to the spring glass problem, which are like, oh, maybe not so many people are interested in. Okay, so I said, okay, let's invest in this, and let's see how we can move forward, right, with this idea of like, how can I make sense of all this data, right? And we started thinking, and actually I got a paper, I have to say, for review from PRE. And it was this person trying to do this sort of like Bayesian whatever for modularity. And I was like totally clueless. I was like, what did they send this to me? And it took me a few days to read it and to understand what this person was doing. But then I thought like, actually, this approach is really cool. Right? I mean, how could we use it, right? So we started thinking about, can we build models that describe and predict and observe data? Can we do this? Can we really do this, right? Nobody, at the time, nobody had really thought about this problem. It's like, this is a very common problem in, say, the machine learning community and computer science and in other fields. But for us, it was like, oh, I mean, could we do this? Could we actually develop models that assign probabilities to what I see and then help me obtain probabilities for what I don't see, right? So this is what we wanted to do. And if I do it, I mean, can I use this Bayesian formalism to do it? Because I mean, we weren't sure, right? I mean, we were kind of like, oh, maybe we could do this. I don't know. So we said, okay, let's use probability theory. This is a book that can you read it? Well, yeah, I think so. So this is Jane's book, like Probability Theory, The Logic of Science, should be in your night table next to you. Like you should sleep next to it and then just like get the vibes from it. Yeah. I read even if you read just a few chapters, I mean, this is a really, really good book. And you will learn a lot of probability theory and you will learn a lot about the logic of science and about how to think and why I shouldn't use modularity. Well, anyway, yeah, like things like this. And maybe you will question other things that you've done in the past, but it's okay. I did modularity once and I'm very proud of it. And now I do something else. That's fine. And then we also decided to use these stochastic block models. I'm not going to talk a lot about this now, but we thought like, oh, these models, I mean, this gives me this generalization of modularity because what? So at the time, people were thinking large scale structure of networks equals groups that dense areas in my network. So nodes that are very connected to other nodes, that's it. But there are many other structures that I can think of, but modularity wasn't good at measuring them. But stochastic block models are good at doing that. So they were simple models and they have had many refinements in there since then. But I mean, we thought that people have been using this in social sciences. I mean, maybe we can do it for what we want to do. Well, we could, and now people have done trillions of things with them. But I think for us, right? I have to say, for us, we did this. We were super excited. It took us forever to understand how to do this. I mean, you cannot imagine. I mean, this was so hard. We were not understanding what we were doing. Actually, we made a mistake and we published it with a mistake, and we realized later. But the results, the corrected results were even better than the ones that are in the paper. So fine. A very basic mistake using a Monte Carlo algorithm. But it took us years to understand what we had really done also, right? After reading the paper a few years later, we said, oh, how come we did this correctly? We didn't even know that we had to do it this way. But it just, I don't know, we happened to do it correctly, like good for us. But I mean, at the time, really, it was hard, but we decided we're going to invest in this. And we really think that this is the way we should do it. And we've learned with time, right? Years later, many years later, right? We decided to use this to other, we have done this with many problems. And one of them is to try to predict mechanisms of interaction between drugs. So let me, and this is just an example, but I think it's a nice example of how you can use these tools that you learn from, you know, very fundamental problems, whatever it is that you're doing. It doesn't have to be networks. It is whatever it is. It's stochastic processes, it's chaos, I don't care. But sometimes you can find applications in something that really matters and in some really cool data sets. So now, in recent years, right, well, until, you know, not so recently, the people were using, say, these single drug treatments for many diseases, including cancer, right? But since, say, like 10 years ago or so, they started using more and more combinations of drugs because they can have what they, different types of effects, and what they prefer is this sort of synergistic effect, right? In which the effect of two drugs at lower dose is the same that they would have, right? If they had only one drug at a much larger dose. So this is very interesting because of secondary effects, because of, like, if you give something that is chemotherapy-like and suppresses the immune system, you want to give them lower doses for many reasons, right? Now, this it's very hard for, like, pharmaceutical laboratories to find, like, the pairs that are going to interact in the way you want. And this is where computational methods come into the question. So we participated in a challenge. This is one of these dream challenges that AstraZeneca, before doing the vaccine, was working on. And they had this prediction challenge. We decided to participate, and we developed, this is the kind of data, what it looks like. And we developed models based on stochastic models to predict interactions between drugs, right? And it's not a simple network. Like, the thing is that in here you have observations for many different types of cancer and many gaps in your data. And what they were asking you in this challenge was like, okay, for this interaction with these two mechanisms in cell line XX for, like, I don't know, lung tumor, is it going to be synergistic or not? This is the kind of thing that they were asking you. Well, using this kind of models, this was super exciting for me. We could, I didn't put the results in here, but what we did was we classified among the top 10 teams in the world, only using network data. Like, the people who did very well were people who are like biochemists and pharmacists, and they were, they knew very well the properties of the drugs and everything, but we did nothing. Clearly, I'm not a pharmacist. Roger is not a pharmacist. The other people doing this work, they were not pharmacists and not biologists. No, we are just like, I don't know. We barely know what we are doing, but we know how to deal with networks. And we used this, and we did very well. And we even went on TV for this, imagine. Well, anyway, cool. So my lesson here, all this didn't happen in one day. It took us like 10 years almost of our time to do anything like this. So when you have a project that really matters, it's going to take a long time. And it's easy for me to say, oh, you have a position, whatever, but I invested on this when I was still a postdoc. So just don't close your minds. Good science needs time. And it doesn't need a lot of papers. It just needs good papers, I think. All of our papers have taken a lot. They are like our babies when they are born. And it doesn't matter where they have been published. I mean, they are a lot of work and a lot of love, that's for sure. Well, anyway, so moving on, almost there, almost a machine scientist, yeah. So one thing leads to another. And then we suddenly thought, well, suddenly no, as I will tell you in a little bit. We thought, what if my data is not a network, right? What happens if I have other type of data? What can I do with this Bayesian thing that I like so much? Can I do something with it, right? So one thing, well, here Is that right? Imagine that I have these data points and I could feed these to different models, right? Some people would say that the model at the bottom looks kind of nice. I mean, it's closer to the point, right? But we would all, you all agree with me, that we would all think that the straight line is a better model because it's a simpler model, right? It's close enough to other points. And also because in my mind, you think, if I had another point, right, probably the line would give me a good prediction for another point. But this other funky model here probably would be a little off, right? This is our intuition. It's like, it's not only that it's simpler, also because probably I think the capacity of this model to extrapolate is better. Yeah? So from this, right, we did this. This is not a picture done by me, but this is a very pretty picture. This is a picture done by an illustrator for Quantum Magazine. But I mean, we build our machine scientists, right? Our machine scientists will take data, you crunch it, and then it spits out mathematical formulas that explain, right? But it's not only just any mathematical formula. It's mathematical formulas that explain well my data and that are parsimonious enough. Okay, so what time is it? So do you want a break if I move to the next part? Or I mean, I don't want to keep going. We have we make like a 5-minute break or not? Is it like? You want a break? Yeah, you do? Or not? Should I keep going?
It's a very interesting part.
I can go. Okay, so I'll go. Okay, so let me see slide. Okay, so now we are done with my life and why did I decide to do the thing. And now I'm going to tell you about the machine scientist. Okay, let me see why. Okay, here. Okay, cool. Do you know who this person is? Does anybody know who this person is? No? If you don't, it doesn't matter. So this person, probably not. I mean, I don't think, you know. This person is Tycho Brahe. So some of you are like, oh, well, I mean, before, I mean, I know who he was by name, but not by picture. But so this person at the end of the 16th century was an obsessed astronomer, I should say. So he started collecting surprisingly accurate data on the position of planets and stars in the sky. Okay. So he was a Danish astronomer. But he was born in Sweden. Well, anyway, I read about him. Well, at the end of his life, for some reason, he moved to Prague and Germany, and there, a very young Johannes Kepler started collaborating with him. And when Tycho Brahe died, Johannes Kepler took on the grueling task of finalizing the collection of data of stars and planets in the sky. And he did not only do that, probably he did a lot of data analysis by hand. It must have been a lot of work, right? Like he looked at everything by hand. And he came up with what we now know of Kepler's laws of planetary motion. And he, like, there are a few, but for instance, he could relate the period of an orbit, right, to the radius of the orbit, for instance, right? And that was it. And not even 50 years later, this person, Isaac Newton, he proposed his law of universal gravitation, and it turns out that Johannes Kepler's laws stopped being, say, phenomenological because they could be derived directly from the laws, right? So, and actually, in the work that he did, that Newton did at the beginning, he used this as like, you see, like my law of universal gravitation predicts these laws. So, I mean, it has to be, it's like, you know, an added bonus, right? I mean, it has to be correct. Well, anyway, so why am I telling you all of this? Well, I'm telling you this because, I mean, so now we have lots of data, as I said. The sea of biological data and of social data and of any kind of data is still out there. And our goal was to develop some tool that would do the job that Johannes Kepler did in here. I mean, I don't want to be somebody who develops like fundamental theories, but I wanted some algorithm that would help me extract phenomenological relationships from data. Okay, so I look with a little bit of luck, if I have this sort, which I won't, but if we had this sort of wealth of phenomenological models, they can help us, right, understand what are the underlying, like, more fundamental mechanisms that explain these phenomenological laws, or they can help us understand what are the relevant variables, or they can help us understand limiting behaviors, what have you. But we wanted to develop something that would be able to do this. Yeah, and I will tell you what we have developed and show you examples into context of this, say, complex problems. We have lots of data and nobody has been able to find a mechanistic explanation for them. So this person is Nikuradze. In 1933, almost 100 years ago, he did these experiments on rough pipes. So what did he do? He also did a lot of work, and he coated different pipes with grains of sand of different radiuses to mimic different roughnesses. And he just had fluids flow through the pipes, and then measured what he called the friction factor, which is essentially the loss of pressure, right? As the fluid flows through the pipes and it's rough, there is friction and you lose pressure, right? Okay. And then he plotted friction factor in the y-axis, and then the Reynolds number in the x-axis in a logarithmic scale. And he had this area here, this line, which is like laminar flow. He understood very well this. And then he had these other funky curves that would separate. They would be different for each one of the roughnesses of the pipe. And people couldn't really understand. They have not been able, so they have Navier-Stokes equations, but they have no clue how to get to this. They don't know. They cannot explain this in a way. They cannot explain this from using fundamental fluid mechanics equations. Okay, this would be problem number one. Problem number two is a more, it's not such a fundamental problem, but it's an interesting problem. So it's that of, so now we are, and if we are not, we should be very worried about what we are, throwing to the air, or all the trash that we are putting in the sea. Well, so we teamed up with people from ETH to try to understand whether we can predict at a country level what the environmental impacts are going to be in terms of so for instance, energy consumption or CO2 emissions or emissions of other greenhouse gases as a function of other macroscopic, say, socioeconomic drivers, right? So for instance, population, GDP, active population, urbanization rate, climate, sort of weather or temperature. And our goal, as always, is to see, can I make models that make predictions on this for each one of the countries? And can I, if I do, can I see how these emissions depend on the variables that I'm putting, right? Can I have sort of the derivatives? In economy, they call them elasticities, which is sort of a logarithmic derivative. But the idea is can I know how much an impact is going to change if I change any of the independent variables in my country, right? So maybe we can help policy making. Well, anyway, let's see if we can do this. Two very different problems, but two problems of the same kind, right? We have all this data out there and we don't really know what to do with it. Well, we do things with it, but I mean, well, let's see. Okay. What's the common point to these two problems? I'm checking my time because I'm going a little slow. So the common thing of these two problems is that we want to find a function, right? Of X, say my independent variables, like for instance, the environmental drivers, right? And some parameters, right? That gives me a value for the variable that I'm measuring, for instance, CO2 emissions, right? Yeah. And this is the common part. And what I want to do, right, is to design what we are going to call a machine scientist that automates this task, right, of building mathematical models from the data. And what do I mean by a mathematical model? Because everything I don't know, a neural network is a mathematical equation, right? I can write the equations. It's a lot of equations, but I can write them. But what I'm talking about is this kind of models like this. The linear model and the very complicated model on the right, right? This is the kind of things that I'm looking for. This is what I call a closed form mathematical model, right? Okay, so this is what I'm looking for. Okay, so now, and this is my machine scientist. I already showed you this. If somebody wants to read the Quantum Magazine article, it's a nice article. These people write very well. They really do. And you will learn about things that unfortunately cannot tell you about in here. I will tell you about only one because it's relevant to the story of this machine scientist, okay? So, okay, how do I formalize the problem? So let me go back in time again. We go back to 2009. I was still on Northwestern, but living or thinking about living. No, I had already gotten my position, but I was very pregnant, so I was still there. And we found this paper in Science. So these people, Schmidt and Lipson, they had this data on the double pendulum, right here, and using what they called genetic algorithm-based symbolic regression. I didn't know what this meant, but I will tell you in a little bit. They were able to detect conserved quantities, like for instance, conservation of angular momentum, right? And I remember we said this and we talked about this and I was like, how can these people do this? Isn't it amazing? I mean, they input this to this like algorithm that I don't know what it's doing and it outputs a conserved quantity. Like, well, I don't know if you are surprised, but I was like super surprised. But at that time, I was like, okay, these guys are very cool and they, you know, they really know what they are doing. And well, maybe I don't know what I'm doing. But later on, we tried to use it for another problem. And we were growing very frustrated with it. And we decided, well, maybe, can we do something maybe that's a little bit better than this? So let me tell you a little bit about what this was doing, right? So now the first thing, so this is genetic algorithm-based symbolic regression. So symbolic regression is this idea in which like in a regression problem, right? I want to find the best model parameters that fit my data, but in here, I do have two sorts of different variables. One is the model parameters and the other is the shape of the mathematical model, right? So I have these two things that I'm looking for. And the thing that it's like really like the genius thinking of these people is like, oh, we can represent equations as trees, right? So I have a tree and in each node, I put either an operation or a variable, okay? So for instance, if I have y equals z plus 2 sine of z, then the first node is a plus, then it has two children. In each children, I put each one of the elements of the sum. But if one of the elements is more complicated, like 2 sine of z, then I have a product, and then I have one child, and the other one is the sine that has an only child, because it's a function of one only variable. Okay, so I can represent it like this. This is very nice. If you're a statistical physicist, it's very appealing, right? Because now, and if you're not, also. Why? Because whatever you are, it's super appealing because it means that then I can think of algorithms to generate other mathematical functions, right? I just have to start changing different elements of my tree, right? If it's a variable, I can change it for another variable. If it's a parameter, I can change it for another or for an operation, right? So I can change a plus by a minus or by a product or by something else. Or I can change, for instance, complete terms, right? I change this one term, this 2 sine of z by another one, whatever. And then I can swap them, right? So what they did was, we have this genetic algorithm. I don't know if you know how they work, but the idea is that I have several copies of my system running simultaneously, and I allow different operations. Some operations that are internal, like the mutation one, and some operations that are like cross-breeding operations. So I get one part of the model and I put it in the one below, and part of this model and I put it in the other. And I keep going. So cool. Now I have this very nice way of generating mathematical formulas. This is actually very, very cool. Very, very cool. Because I mean, until then, nobody knew how to do this, right? They were doing other things like assuming that my base is a sine plus x squared plus a term that is x to the 3 halves plus another one that is exponential. And I try to fit my parameters. This is what people were doing. But this is so much better than that. I can generate whatever I want. Now, but there are some questions, right, about this. I don't know if you have thought them, but I have, so I'm going to tell you. So first one is like, so now how do I define what's a good model and what's not? Because in my algorithm, I don't see it. I mean, these people are changing here and it looks pretty random to me. So I have to define this. And also I have to define this idea of parsimony, right? What's a simple model and what it's not here. So I want to define it. And also, in the end, I need to balance the two. So what happened with this type of approaches is what they ended up with this black line, which is called what's called the Pareto front, right? So if, for instance, I fix the parsimony or the complexity of my model, then I can find the model that has the lowest mean square error or the log of the error, whatever it is that you define as a goodness of fit, right? But you end up having a lot of models, and then you have to decide which one to pick. And also, the complexity, it's heuristic. I mean, I can decide, a sign can have a complexity of 1 or of 3.5. I don't know, I can do whatever I want. So we were kind of like, well, I don't know what I have to put in here, and which model is the best one? Is it the 2 in the black square, or is it any other model? So it was, sorry, it was for us, it was kind of frustrating. I mean, why do I have so many models? I just want one model. Well, probably it turns out that this is unavoidable, but there are better ways to go about this. Sure.
If this is a Pareto plot, then it is a complete Pareto plot.
Probably.
Then we have continuous transition in your search.
Because they were not, so this is an a posteriori Pareto front. They are not trying to find the Pareto front. They were just like generating models. Yeah. They were generating models with their algorithm, and then they were saying, oh, with this complexity, which models have I found? Oh, this is the one with the best goodness of fit, and this is the one that they were doing. But they were not, I'm saying they end up with this sort of Pareto front, but they didn't have a cost function like a Pareto, like a multi-objective cost function that would give them this. Yeah. So it's like they didn't solve the multi-objective like optimization problem. It's an a posteriori kind of thing. Yeah.
Imagine that a very good formula that explain that to get to a very good formula that explain data very well, you have to pass by the whole speed through some expressions which eventually give a good formula but are super rapid to get data. So you would have to pass through like very high state. How will you do that?
Well, I mean, as I said, they didn't. This is the genetic algorithm symbolic regression, and they didn't have this problem because they were not defining a cost function from the start. They were just sort of like generating models and see then what's good, which was, in my mind, an awful thing to do. What I will explain later with the machine scientist has sort of like this problem that you are saying, and maybe we can talk about this later. But they were not having in this genetic algorithm that there was no cost function. They were just generating models, and then, well, they did have some fit function, but I mean, they were not trying to solve this like multi-objective optimization problem from the start. It was more like a posteriori. It's like, well, now we have collected all these things, okay, and then we look at it. Well, anyway. Maybe they have other papers in which they have done other things. I'm just talking about this one, but their software still has the same problems. So that's probably the last version they have of all of it. Well, anyway, so let's talk a little bit now about we'll talk a little bit later about the hills and the problems that this has. So now the other thing that bothered us is that we didn't know this exploration of the space of models, right, was very heuristic, right? So we didn't know if there were holes in the system that they were not exploring. There was no assurance that they could explore the whole space. It was kind of crazy, and it's not a problem if what you want is to optimize some cost function. It's fine, you can explore whatever you want. But it's an issue if what you want is to get like averages of this ensemble of models, because then you can't, because it doesn't have the nice properties that you want your ensemble to have. And I hope that in a little bit this will become clear. So, okay. So we were unhappy with this. And we said, okay, so what do I want my machine scientist to do? This other algorithm is very cool, but it's not doing what I want. So what do I want it to do? So what we wanted to do, and I think I will have to cut because yeah. So what I wanted the machine scientist to do was, okay, I want something that actually can estimate the plausibility that if I have an observation, a certain mathematical model is the one that generated the data. Okay, this is, let's wish, right? I want this to happen. I want to have an estimation that, I'm going to say it again. If I have some data and some observation, right? I want to estimate the plausibility that the model F generated this data. I want to estimate this, right? And with this, yeah, my best model will be the one that is most plausible, right? If I can do this, the best model is very well defined, right? I estimate possibilities, the most plausible model, it's the best model. I don't have to worry about other arbitrary things. I want this to be set from the start because it makes me feel very safe. And I don't have to justify anything. This is the way it is. This is probability theory. Okay, so let's go with it, right? So we use for this, right? We use what we call Bayesian model selection. I will talk a little bit about this Bayesian thing, and maybe some of you are very familiar and some of you are not. So what you're trying to do, how do you estimate the plausibility of a model M given data D? So what you do is you use Bayes' theorem and you express it typically in terms of the likelihood, which is the P of D given M, which is essentially the probability that my model generated the data that I see. Okay, and if you have a generative model, you can obtain probabilities for every observation. Good. Then you have the prior. The prior, it's very important because it's my a priori belief that the model is correct. And this is where, as scientists, right, we know that some models are more plausible than others a priori, right? Because I like lines and exponentials, and I don't like logarithms of sines of x to the 3/8. This is very strange. So these models, I want the algorithm to know about this. And then we have the evidence, which in our case, it's like a normalizing constant. Okay. So it turns out, and now this is a little bit mathematical, and probably I'm going to skip it, that in my case, my model, this abstract thing that is my model has two parts, right? The tree, and then the values of the parameters that there are in my tree. And because what I'm interested in is not the values of the parameters, but the tree itself. What I have to do is integrate over parameters. Well, don't worry too much. You get these expressions, and you can do it. You have to believe me on this. You can do this. You can estimate this integral. I will tell you how. And you can end up having that your plausibility, what you're looking for, right, is an exponential of some quantity divided by some evidence. Okay. So again, as a statistical physicist, I love exponentials. Like, don't even get me started. It's awesome. I have an exponential. I can do a lot of things. I love it. Like the first thing I can do is that this function L here, it looks like an energy, right? Yeah, it's like my energy here. So this L is my energy, the energy of my model and my data. Actually, this has information theoretic also interpretation. This is not an approximation. This is equal to what's called the description length in information theory. So what's description length? Who here has heard about description length? Okay, quite a few. Probably you know better than I do what description length. But for those who haven't, so the idea behind description length, right, is the amount of nuts in this case, because I'm taking the natural logarithm based, that it takes me to describe the model and the data. So now, very compressive models are very good at describing me the model and the data with very little information. And compressive, and these have very low description lengths. The ones that have low description lengths, for instance, writing every single point, right? This would have a very long description length, and these are not preferred models, okay? So description length, it's the same idea as in energy, right? Minimum description length, minimum energy. Those are the best models, the ones that will give me a larger plausibility. And it turns out that I can estimate the description length, right? And I can estimate it as, which means estimating this integral and taking the logarithm of this integral. It turns out that there is a thing that maybe some of you have heard out of, which is the Bayesian information criterion. So the description length has a part, which is the Bayesian information criterion. This can be computed from the data. We don't have to worry about it. It's easy to do. And then we have the logarithm of my prior, okay? So here I have two elements, right? The Bayesian information criterion and the prior. Now it's not true. So the Bayesian information criterion comes only from the integral of the likelihood part, which is the part of the data. So the Bayesian information criterion, it doesn't have these two parts that balance goodness of fit with complexity of the model. No, it's not true. It comes all from the same part, and it comes from the data only. And the part of the complexity of my model comes here in the prior, okay? And if you don't put it, you're in trouble because you don't know what are simple models and what are not. And you're in trouble, in the same trouble that the genetic algorithm was. Okay, cool. So now, how do I select my prior? So this is an arbitrary choice. Okay, you have to select find a way to estimate complexity. So what we did is we went to Wikipedia, right? So our idea was like, oh, where can I find intuition as a scientist, or where do I get it from? I get it from the examples I've seen in my life, right? So I've seen many exponentials, many products, many things that I know make sense for natural laws, and some things that I've never seen in my life, which are very implausible for me as my brain as a scientist. So we went to Wikipedia and we got all this corpus of mathematical expressions for natural laws, okay? And from there, we looked at, well, how many times I see a sum or a product or a this and a that, right? I looked at the distribution. And then my prior, I wanted my, what do I want my prior to do? I want my prior to reproduce the statistical properties of this corpus, right? From Wikipedia. I could have selected another corpus, yes, but this is the one that I did because this is the one that I know how to parse, even though it took us a long time to do it. Also, another thing that took time, but it was with a lot of love. Okay, so then how do we do this? We use what's called a maximum entropy approach. So in this kind of approach is what you do is you want the distribution that is the least informative, so maximizes entropy, but satisfies certain constraints. And the constraints are given by the Wikipedia corpus, saying I want to have on average the same number of sums, and we had to force it to have the same variance in the number of sums and of any operation that we had. The reason for this is technical, but if you don't do it, you get a bimodal distribution and you want to have something that looks more like a normal distribution. So you have to do it like this. But anyway, we do it. Okay, so then so we have our prior, we have our plausibility, right? We know how to estimate it. Now it comes the part of like, how do I sample my space of models, right? So the idea is that because I have this exponential, right? I can use any algorithm from statistical mechanics to sample over my space of models, right? And I can do this because if I just drawing from what these people, this Schmidt and Lipson did, so I represent my mathematical functions as trees, right? And then I just propose movements and accept them according to some metropolism algorithm, according to the changes in description length. Yeah. So I can, well, decide to change, I don't know, add a root to the top, or I can decide to change one of the children, right? Or a full branch, or I can decide to change exactly, a variable for another. Yeah. So I can propose all these sort of movements and start exploring. Now, going back to what you said, this is a very, very rugged landscape. It's hard. I mean, it has lots of hills, very high hills. It's complicated. But what I can do it, what we did to try to mitigate the fact that you can get, stuck in a center, we did this technique which is called parallel tempering. Any of you has heard about this before? Parallel tempering? No, this is old things. So the thing is that you can run several copies at different temperatures, meaning that at high temperatures you accept no changes, but then you accept changes between the different replicas at different temperatures. This is something that I learned during my spring glass days also. And the thing is that it helps you investigate things that happen at lower temperature by exploiting the fact that at higher temperatures you can explore different minima. Well, anyway, if somebody wants to know about this, you can write to me. So we use this. How does it work? And before, I will not, well, no, let me show you how it works first. So now I'm going to show you. Okay, cool. This is a video. So what I'm showing you here, right? It's a function of two variables, right? And the surface here shows me like the model, how it's evolving. The two plots here show me the description length that it's, as you see, it's getting lower and lower, and the mean square error of the model with respect to the observed data, right? And as you see, right, the shape gets closer and closer to the points, and at a certain point, because this is an easy problem, right? It gets sort of like stuck at visiting models that are very similar to the correct one. And these ones here are the parallel tempering results. Well, so my sampling algorithm works. I can find the point of the model. Oh, I'm very happy, right? My model is working, right? And just to, let me stop this. I go back. So here, I know I'm just like abusing of my time here, but so that it's clear, right? Why is this approach that we did better than what there was before? And why it will enable us to do other things that were not possible before? One, it's because since I'm using this Bayesian probabilistic approach, I don't have to define goodness of fit. I don't have to penalize model complexity because I'm putting this already as an ingredient in my model. And I know exactly how I'm putting it. And it's always in the same way. So I know why I should be getting out of it, what I should be getting out of it. Okay. Now I don't need to balance artificially goodness of fit and complexity because again, it's something that I get directly from Bayes' theorem. I know how I have to do it. And then the other is that I can sample directly from this, as in here it says posterior. Essentially, I can sample plausibilities of models and I can obtain whole distribution over models. This is very cool because as we will see later, you need it to make predictions for like complex data because typically you have more than one model that is good for your data, not only one. Okay, so let's go to the examples. And I probably will explain only one and skip just the last part. Let me show you the results for the Nicolatz's pipes. Okay, so I remember we looked at the data. Actually, Roger Guimarães had to go to the paper, the original paper, right? Put it in the screen and get the axis and everything and get the points like this because there was no table with the points. But then we checked with other people who had done the same and they looked to be like correct, like whatever. So we have the points now by extracting them from the plot directly, which was awful. But here we are. So we run our machine scientist, right? And here I'm showing you is the friction factor, if you remember, right? The loss of pressure, right? Versus Reynolds number. And I have removed the linear, like the laminar flow regime because that's not the interesting part. The interesting part is this turbulent flow here. Okay, for higher Reynolds numbers. So now, look at this. So gray points, data points, red lines, machine scientist output. So nobody here, the two models are awful, by the way, but no, I don't think that anyone can tell me that one model is better than the other. They all look pretty good to me. I don't know which one is better. And the plausibilities are very similar, right? They are similar enough that any person with a common sense would not be able to tell one from the other because there is noise, blah, blah. So why are there so many models for this? We were kind of like, so there is not one? I cannot find a very best model? Wow, the machine scientist is failing. I mean, it's not, we thought we could get like a very good model and we're not. But then we said, you know what? So there are many models, okay? So in this range of data that I have, there are many ways in which I could explain this data. Some have errors here, some have errors there, but overall, I cannot tell you which one is better than the other. But, I have this collection of models and maybe I can put it to good use, right? Because so we know this, we know the power of ensembles, right? We know that if I make an average, right? And probably the predictions are going to be much better than if I get just one of the models, right? No, especially when I'm not sure which one of them is the true model. So then we did this sort of machine learning, computer science, say, typical experiment in which I observe the gray points, right? And then I make predictions on totally unobserved data. So one is, so remember these different lines here correspond to different roughnesses of the pipe, right? So the first experiment was an extrapolation one, right? So I get the actual is the lowest roughness because it's the inverse of the roughness. And then I try to see if, fitting whatever, 3 different models. We use a Gaussian process, the yrECA, which is the software of this genetic-based symbolic regression, and another symbolic regression approach, which is the orange, another one. So the red line is the one with the lowest error, and clearly, by a lot. Some of them, they are pretty bad. They are very bad at extrapolating. Okay, so first test passed. The second test is the same one. So you see it's a different kind of extrapolation, right? In which we try to predict for very large Reynolds numbers. And again, right, for the machine scientists, seems to be predicting better. But this is not the prediction of one model. This is the prediction of the ensemble of models, right? So I get a point, a Reynolds number value, and I evaluate it. What's the Y for many models, right? And then, Reynolds number and roughness. And then I evaluated the models and I take the average, right? Like we do in statistical mechanics all our lives, right? That's what we do. And this works wonders, right? So lesson learned from this. It's like, so the problem that they had, the different many models, we still have it, and it's unavoidable. There is nothing you can do. We don't have the tools with this data to find the best model. We would have to have more data points, and experiments in a different range of Reynolds numbers or for different roughnesses. But for this, with this information alone, this is the best you can do. Well, I can live with it, but we still thought like, oh, but I really wanted to learn something from it. So we went, right, and said, maybe, I mean, is there something else I can do to learn more physics about this system, right? So then we went to look at the different studies that have been done on this data. And one of the studies, what these people do in fluid mechanics most of the time is that they want to look for what they call adimensional variables, okay? So they want to find these variables, this collection of products and divisions and exponents of the different relevant variables in their system that are adimensional and that, you know, are explanatory, or in a way they can make collapse all the different curves, okay? So we found several examples of this. The oldest one, which is the one that I'm showing here, was by Prandotu. This old name, important name in fluid mechanics, if you are into it. If not, well, this is the name of the person. And he proposed something in the 1950s. And since then, there have been many other scalings proposed for this with different collapses. The problem is that sometimes they stretch the curve so much and the range of values are so large that everything looks like it fits very nicely. But when you have 12 orders of magnitude, everything looks thin. So, but now the thing is that the machine scientists gave us the opportunity to try fit models to the scale data and then descale the data to see which ones were working well. Now I'm just showing, like, here is like the scaling for plan. It looks a little thick in some areas, but it looks like okay. And then we descaled it, right? We fit the model. This is the model that I got, which here is actually a very nice model. It's just an exponential model, right? With very little complication, right? That depends on the scale variable here. And we descale it and it looks very nice. And all the other models that we tried with one model scales looked awful, awful. So these people were cheating like crazy just by, you know, just plotting it with enough orders of magnitude that their data looked good. So, well, this was our success here, right? So the machine scientists can actually do more things. They can do predictions, they can get models, and they can help you discriminate between models, which is a very nice thing to do when you have competing models to explain your data, right? And so I think this has to be over almost. So I will just give you the last example and skip the last part. So the environmental drivers. So this is the last example. So now imagine I have all this data on population, temperature, surface temperature, urban rate, which is the fraction of population that lives in a city, and GDP, and other things that we're looking at. And I want to predict something like CO2 emissions per country. There is a model that does this. This is a model that was developed by economists, and it's called the Stirpat model. It's a simple model in which I assume that CO2 emissions are just a constant times a product of the different drivers to an exponent. Okay, it's a very simple model. It's a linear model in logarithmic scale. Economists love it because it has constant elasticities, which means constant logarithmic derivatives and changes of variable y are always the same given the change in variable x. Okay, good. So let's see, right? So we are going to run our prediction experiment, right? We're going to run the machine scientist. We're going to see what model we get. We're going to try to make predictions and see if we do better than the Stirpat model or not. And if we do, let's see what the elasticities are. What do we learn from this? So now, first thing, this is not very spectacular, but it's a proof of concept. So I'm showing you here a scatter plot of the predicted value by the models, right? And the real value. Both the Stirpat and the Bayesian machine scientists behave similarly, right? But the Bayesian machine scientist is a little bit better, just a little bit better in any metric that we could find. Now, the important thing doesn't come from the model that we got, which we have models for each one of these things. But the nice information here was that because, okay, in here what we do is we fit a unique model, but each country has different parameters, okay? So then the elasticities are different for each country. And we have a distribution of elasticity. So what I'm showing you here is this elasticity change in CO2 emissions when I change any other bias, for instance, like the GDP or the temperature or the active population or the total population. And I see that I have distributions, but in some cases, oh, I can point now. In some cases, like for instance here, right? I even have a change of sign. So this is like the black line is the Bayesian machine scientist average. The turquoise here is the Stilpat average. They are quite close, but then we find these very broad distributions, which means that for some countries, changes in, this is the urbanization rate, has no effect, no impact in CO2 emissions. And for some countries, it's huge. And for some countries, it's even negative, right? So what was the, so this was published in the journal about sustainability and whatnot. But the thing is that what's important for them, right, is realizing, which we all sort of knew before the start, but not all countries are equal, right? And different policies are going to have different impacts depending on where you are, right? So the value of these models is not the model itself, right? It's just getting them thinking, oh, well, maybe just using this kind of approach it's nice for economists, but it's not actually going to get you very far. Okay, so I think that was it. I had other things, but I think it's too much. We started late, but I think this is enough, right? Well, I mean, we have a coffee break, right? I mean, unless you want me to keep going, you know, I can pull other seminars if you want, but I mean, it's not like no. I think this is unless somebody really wants to know something about learnability, which maybe not some other day. Actually, there is somebody in my lab who's going to give a talk about it in the conference. So what about that? You go to the talk and then you learn about it. No, it's not Joyce. No, it's not Joyce. It's no, Joyce does he's doing a PhD in our lab. You should go to his talks about science of science, which I didn't talk about today. But anyway, so yeah, so Oscar Fajardo is going to give a talk on this, and I just like, yeah, I just will take. So let me go. Yeah, I have lots of things in here. Just acknowledgements of people who have collaborated with me on this, right? So Virgili, with whom I co-direct the lab, we are the two senior people. We have worked a lot of years for this. I mean, you are not imagine, like last class on this is like, we have asked for funding so many times for this, and absolutely nobody gave us money to do this. But we still decided that we wanted to do this. And it turned out okay, right? We got a very nice paper, well, several nice papers in the review in very nice places. And this was our dream for such a long time. You know, I started doing this when I was pregnant with my second child, and she's now 10 years old. So this has been a long time, right? But really, I mean, I don't know, in the heart of a scientist, and for you who are young, just don't keep the drive that keeps you. Don't lose the drive that keeps you going. I mean, it's important to believe in what you do, and no matter what reviewers tell you of projects or of papers, just go for it. I'm sure there are so many things, and you will be proud of what you've done when you're done. Okay, so that's it. Thank you.